Welcome friends. In last few lectures we have seen various aspects of short transmission line and medium transmission line. Now we shall see long transmission line, its analysis part, voltage equation, current equation and ABCD parameters of long transmission line. What is long transmission line? It's spanning more than 250 km long and we use mostly distributed parameter model for better accuracy. However, lumped parameter model can also be used for analysis part of long transmission line. It has been used in many cases. So let me going through the analysis part. So this is a long transmission line, 3 kilometer long. Let us say we have a impedance and we have a admittance. And we will consider this part for a very small distance, say dx, right? We have sending end voltage Vs, we have sending end current Is, we have receiving end voltage Vr, we have receiving end current IR. As this length is only dx, so series impedance should be zdx and shunt admittance should be ydx. Now the voltage is appearing across just before this section, let us say this is V plus delta V, and voltage appearing across just after this section is V. So we can write voltage drop in the section is V plus delta V minus V, that is equal to delta V, or you can say dV, or you can write more general term, it's dV, right? V plus dV, you can write this is as dV. Similarly we can assume the current entering to this section I plus di and current leaving this section is I. So current flowing through I is actually, it is entering I plus di, it's leaving I, so it is actually di. So this much amount of current is flowing through this shunt admittance. The total length of the line is L. Okay, and we are standing at x distance. From sending end. So first of all, let me write down what can be written as dV. So dV can be written as current flowing through this branch, that is I plus di, that multiplied into z dx, and that is nearly equal to I into z into dx, because di into dx term is neglected. So we have from there dv by dx, that is equal to I into z. Similarly, the current flowing through the shunt admittance di can be written as v into y dx, v into y dx. So from there di by dx is v into y. So this is one equation, dv dx is equal to iz, and this is another equation, di by dx into is equal to vy. So with these two we write d2v dx2. From there, from the first equation, we take the another derivative d2v dx2, that is equal to z into di dx, or d2v dx2, that is equal to z into, now what is di dx? Di dx is y into v, so y into v. So from there we can write d2v dx2 minus yz v, that is equal to 0. It is second order differential equation, and its solution, if you write, it's equal to v is equal to a1 e to the power gamma x plus a2 e to the power minus gamma x. A1 and A2, that is constants. We need to evaluate those values A1 for A1 and A2, and gamma is basically nothing but root under yz. Gamma is equal to root under yz. One new parameter, it's called propagation constant. It's called propagation constant. So from this equation, so if you take another derivative, so dv dx from this equation, dv dx, so you see the first part becomes a1x into e to the power gamma x, not x, it should be gamma, a1 gamma e to the power gamma x minus a2 gamma e to the power minus gamma x. What is dv dx is equal to? What is dv dx equal to? dv dx is equal to, you know, I into z. dv dx is equal to I into z. So iz, that is equal to a1. Now let me write down what is gamma is equal to. Gamma is equal to root under yz into e to the power gamma x minus a2 under yz into e to the power minus gamma x. So I is equal to a1 1 upon root under z by y into e to the power gamma x minus a2 1 upon root under z by y e to the power minus gamma x. So this equation can be written as I, that is equal to a1 into zc a1 into gamma x, a1 into e to the power gamma x minus a2 into e to the power minus gamma x that should be multiplied with 1 by ZC. What is ZC? ZC is called root under Z by Y. It's called characteristic impedance of the transmission line. Characteristics impedance of the transmission line. So we have I into ZC, that is equal to A1 e to the power gamma x minus A2 e to the power minus gamma x. So we have two equations with us. We have two equations with us. But what are they? Equation number 1 is V is equal to A1 e to the power gamma x. V is equal to A1 e to the power gamma x plus A2 e to the power minus gamma x. A2 e to the power minus gamma x. And second equation we have I into ZC, that is equal to A1 e to the power gamma x plus minus A2 e to the power minus gamma x. I have done one mistake. Actually this x is not considered from the sending end, but x is considered from the receiving end. So this length is actually x. It is situated from receiving end, right? Not from sending end. This is x. So that means x0 means x is equal to 0 means we are standing at receiving end. We are standing at receiving end. And x equal to L means we are at sending end. Now from these two equations we can write, if x equal to 0, what does it mean? At receiving end. So at receiving end means V is equal to VR and I is equal to IR. V is equal to VR and I is equal to IR. Okay. So let me substitute. So V is equal to VR, that will be equal to A1 plus A2. And I is equal to IR, so IR into ZC, that will be equal to A1 minus A2. So if you solve these two, A1 will be half VR plus IR into ZC and A2 will be half VR minus IR ZC. So we can write V is equal to half VR plus IR ZC e to the power gamma x plus half VR minus IR ZC e to the power minus gamma x. So with that we can substitute. If you take VR common, so we have e to the power gamma x plus e to the power minus gamma x by 2. And if you have IR ZC common, then within bracket e to the power gamma x minus e to the power minus gamma x by 2. So V is equal to VR. This can be written as sine hyperbolic gamma x. Okay, even before that, I am coming to that later on. and from the current equation we can write I into ZC. Okay, now now if we with this equation if we put x equal to L, that means at sending end, we are at sending end. So with this equation we can have V is equal to Vs, that is equal to Vr e to the power gamma L plus e to the power minus gamma L by 2 plus IR into ZC e to the power gamma L minus e to the power minus gamma L by 2. And that is equal to Vs is equal to Vr sine hyperbolic gamma L plus IR ZC cos hyperbolic gamma L. So this is equation. This is your first equation. Now with the current equation, I into ZC, with the current equation we can write I into ZC, that is equal to A1. So what is A1? Half VR plus IR into ZC, A1 into e to the power gamma x, A1 into e to the power gamma x minus half VR minus IR ZC e to the power minus gamma x. So again we will do the same thing. If you take VR common, so it will be e to the power gamma x minus e to the power gamma x by 2, and if you take IR ZC common, then it will be e to the power gamma x plus e to the power minus gamma x by 2. So at x equal to L, so we are at sending end, so I becomes IS, so IS becomes VR by ZC, VR by ZC cos hyperbolic gamma L plus IR sin hyperbolic gamma L. So this is equation number 2. So if you compare these two, we can have A is equal to sin hyperbolic gamma L. Now Vs is equal to A VR plus B into IR. So B should be equal to ZC cos hyperbolic gamma L, and C, that will be equal to IS is equal to C VR. So it should be 1 by ZC cos hyperbolic gamma L, and D is equal to sin hyperbolic gamma L. So these are the ABCD parameters for long equation or long transmission lines when we consider distributed parameter model. So with this I am ending my lecture here. In the next lecture we shall explain the meaning, physical meaning of these various terms, that is propagation constant, characteristics impedance, and the behavior or the physical interpretation of the long line equations. Along with, we shall demonstrate a numerical problem on long transmission line with this theory. So I am ending my lecture here. So looking forward for the next lecture to demonstrate the various aspects of remaining aspects of long transmission line. Thank you.